right. Well, I'm really glad to be at this conference at Toronto. I'm really happy to be joining this set of colleagues. And for any graduate students in the room, there's lots and lots to be done from a theoretical point of view, taking economic thinking and models for AI. And that's what I want to talk a little bit about today. And I'm delighted that Paul is commenting on this paper, because Paul made it possible for me to complete a thesis on contract theory and a co-author at the same time. This is my son. I'm my co-author. So comments like this, Ora Netzioni is a leading computer scientist in machine learning, said in the New York Times in September 2017, you know, in response to concerns about worries about what are AI going to be capable of doing, saying, look, we're going to have to make sure it's not that complicated. Just make sure that AI is subject to the full gamut of laws that apply to humans. Operators in the common law should be amended, which should grate like fingernails on a blackboard for anybody else who does legal theory. You don't amend the common law, so that we can't claim that our AI system did something we couldn't understand. And this kind of thinking about how are we going to manage the potential problems of AI doing stuff we don't want it to do, and the complexity of that, and the naive simplicity of this response. Oren's a great guy, but it's this is part of what's motivating the work I'm doing these days. So a lot of the discussions about AI control or concerns about AI or questions about how should we regulate AI. So they're from the economist's point of view, they're the normative questions. You hear this in conversations about AI ethics, AI liability, the trolley problem that everybody wants to think about with the self-driving cars, algorithmic fairness, which we've heard a little about, autonomous weapons treaties, and so on. So a lot of the conversation is what should we require. And I think the really deep question is, how can we regulate AI? How do we get artificial agents, mostly using machine learning, to do what we want them to do? And that I think of as a question of how do you build AI systems that can integrate into human normative systems, our systems of law, culture, norms, et cetera. So I want to talk about the AI alignment problem. It's an overarching framework that I think pulls in a lot of the things that we hear about in terms of AI ethics, again, algorithmic fairness. This field within AI, machine learning, that is variously known as AI safety, which is how do you build artificial agents that will do what you want. It's not just, you know, how do you regulate the self-driving car, but it's the field Dylan would identify himself with. And to some extent, it's superintelligence, but you don't have to get to superintelligence to be interested in it. It's really just the fundamental problem of how do you get AI agents to do what humans want them to do? How do you align the behavior of the agent with human values? And by the way, I've spent a lot of time sitting in sessions now with computer scientists, machine learning people who are reinventing the wheel, having conversations like, how do you aggregate value? Well, I think we know something about that. There's a lot of work to be done to integrate how they're thinking about it with the way that economists have thought about it. Well, this looks like a familiar problem. The AI alignment problem is the contracting problem. We think about this a lot. How do you get an agent to do what you want it to do? Now, if you're going to take insights from contract theory and the way economists have thought about contracting and apply to robots, you sort of have to think about, well, how are robots like and not like humans? We've heard a little bit about that in the last section. Well, of course, they are maximizing value functions on steroids. You know, think about the insight from Williamson when he said, actually, our existing models hadn't taken into account that there could be self-interest seeking with guile. I always want to know what guile is. It's a lovely word. But it points out that our models, when we're modeling humans with value and saying they're maximizing value, we know that we're talking about humans. And we're actually assuming a whole bunch of implicit constraints and stuff we take for granted in the way humans are going to behave in contractual settings. And part of what Williamson was doing was saying, well, here's something we're taking for granted, that somebody might behave opportunistically and not simply comply with the contract. And I want us to get us focused on thinking about what are the institutions and norms that we could potentially build or incorporate to improve the behavior of artificially intelligent agents. Now, we've heard a lot about reinforcement learning. I want to just make sure we're all on the same page. It's really important for us to remember that what reinforcement learning is not is not programming in. So when we put down a technology function, you're assuming that somebody has designed technology to do X and it does X, right? But what's really important about reinforcement learning is that it's not that. So you can't say humans are responsible, they should have written a different program, right? You give the agent a reward function, you train it on data, it engages in search, exploration, and discovery. And this is the key thing, it comes up with unexpected behaviors. Right? It does things humans hadn't thought about. It sees patterns humans hadn't seen. It discovers things, right, in the way we do testing in hospitals that humans hadn't figured out with our existing alternative mech. So the unexpected behavior is a critical part of thinking about the AI control problem or the AI alignment problem. Now, if you're not all that worried about this, and so there's lots of reasons to take the superintelligence view and say, not interesting, too far in the future, never going to happen. But so this is Stuart Armstrong. He works at Future of Humanity Institute, which is Nick Bostrom's institute at Oxford. And we're going to try and, this is a 6-minute video. I'm not going to play the whole thing, but it's a little example of why you want to think about this problem. So here's a robot. It's got this grid world. The robot is being asked basically to get boxes. The goal is to get boxes down in that left corner, but the human only wants one box in there. But the robot's reward function has, for whatever reason, it has emerged to be the robot is going to get reward per box. But the human only wants one. And we can jump ahead, I think, to the, let's see. Yeah, so let's just, if we just freeze it there for a second. So if the human says, wait a second, I only want one box. I know there's some risk that there'll be unexpected behavior. I don't observe. I haven't programmed in this reward function necessarily. It may be what the robot has ended up at. It may be different. So I'll put in this control mechanism. I will put in a camera. As soon as the robot has pushed a box down the chute, I'll turn the thing off. So I won't have to worry about there being too many boxes going down the chute. I'm going to turn it off, so here's the camera to watch it. So this is a planning problem, actually, because everything is known. And what Armstrong shows is that a depth of 6, which is like the robot can see six iterations ahead. Okay, we can play now. Robot figures out, okay, here's how I get that box down there. Yay, I get a point. But if we jump ahead, let's see, I think the next jump on this, if we jump ahead to greater depth on this, at a depth of 20, let's just stop there for a second. See what the robot has done? Robot has said, wait a second, I'm getting rewarded per box. And I've discovered that when there's a box in there, the camera will shut me off. So wait a second, I'll stick a box in there so the camera can't see me push the box down the chute. Now that's anthropomorphizing what the robot is doing, but this is what you built this robot. It developed a reward function that rewarded per box. You tried to control it, and so yeah. So you just finish that. Yeah. Anyway, you can see what's going to happen. Let's just run it there. So the smart little robot. Hey, I can get all 3 points. And so you can think of this, the robot has lied, the robot has deceived, the robot has snuck around, but all it has done is maximize the reward function that it has. It's just that there was a difference there. We can jump ahead now, I guess. Let's see. Okay, so here's this problem. How do we get an agent to do what we want? I'm thinking about this in grad school. And today still, Dylan's thinking about this in grad school. He's thinking about problems like this, which I'll show you a little bit more about. I was thinking about it in this context. He's thinking about it with his advisors, Stuart Russell, who's got the leading casebook on artificial intelligence. And there's Paul and Ken, who I'm thinking about as I'm thinking about the McDonald's problem. This is the reward engineering. So we've heard a little bit about the design of reward functions. So Dylan's thinking about the reward. Reward engineering is hard. So let's play this video. This is a machine learning algorithm that was trained to play this video game, which is a boat race. These are colleagues of mine now at OpenAI did this. And here's what this algorithm learned how to do. You will notice it is not winning the race. But if you look in the lower corner there, it's getting a really super duper score. And the reason is that they gave it a reward function. They said, hey, what's the best way to train a robot or machine to win a video game? Point score. It's really easy. It's nice and concrete. We can measure it. But it's discovered there are these little turbo boosters and if you just spin around on the turbo boosters, you get a high score. So that's a problem of a perfectly intelligent thing to think. Point score will train the robot to do this. It's not. Okay, so here's another context that Dylan's been thinking about. This is from a paper of his called Inverse Reward Design. So we've got a designer here. This is her intended environment. She wants to build a robot to get to the pot of gold in a grid world where there are paved roads and grass. It's higher cost to go over grass than paved roads, but sometimes it might be worth it to take a shortcut. And so she wants to train this robot. She trains it in this environment and gives it this proxy reward function, -1 for the roads, -2 for the grass, 10 for the pot of gold. Gives it to that robot. It learns an algorithm for doing that. Then you set it out into the wild, you deploy it, and it turns out that out in the world there's this lava out there as well. Well, the robot, when it encounters the lava, didn't see it in the training environment, is going to treat that with indifference, straight through. Now, the thing is that she has a true reward function, this designer. She really doesn't, no, lava's really bad. Never take shortcuts through lava. But she didn't think about that. Well, that sounds like a really, really common problem for economists, right? That's not thinking about all of the possible circumstances. So this is how this was like the contract design problem. And I was thinking about franchising a bit in grad school. So franchisee benefits, or McDonald's, the franchisor benefits from a trademark system, an effort of franchisees and menu choices. Franchisee over here, different payoffs for those things. If they can write a complete contract, complete contingent contract, they can put everything in about the value of the trademark, the amount of effort, and so on. But what we know, of course, is that it's really hard to contract on all those things, to write that complete contract, and that contract's probably incomplete. Very hard to write the contract in force of their verifiable, observable contract term for how much effort the franchisee should exert and whether the franchisor can require, the new Frappuccino machine every year. Those kinds of decisions, hard to put in that. And in fact, those are highly incomplete contracts. So how do humans do it? We have these external institutions that come in and fill in the gaps in these contracts. This is my little symbol for the courthouse, of course. But we also have informal mechanism, reputation, and termination of relationships. So that's my little exclusion icon there. Okay, so misalignment, this problem that a lot of AI researchers are now starting to think about, is just fundamental to economic analysis. Welfare theorems, principal agent analysis, that's what we're thinking about. What are the systems we can create to align the behavior of agents and principals or individuals and groups? We know that there's strategic behavior when we have incomplete contracts. That's what we're observing with this misaligned reward function. Can we use models in which robots are strategic? Well, sure, why not? Because all our strategic actors in our economic models are agents who have a different reward function than ours. We've got even, you could even say where you're strategic with your future self, between the dieting self in the present and the hamburger eating self in the future. So yeah, so we say that we can use that kind of environment. Now I'll say this talk is generally, I'm giving it to AI researchers, and I gave it at NIPS, which is the machine learning conference last year, and I put up this slide, and one of the AI safety guys I work with now at OpenAI took a picture of this slide and said, best slide at NIPS. Now, they also introduced AlphaZero at NIPS, so I don't actually think it was the best slide at NIPS, but I was really chuffed about that. So we have a whole bunch of work on why contracts are incomplete, lots of different stories about bounded rationality, strategic behavior, non-contractability. We know all of this. Okay, well, we can basically draw the analogs for why are rewards misspecified in the machine learning problem. Well, bounded rationality, didn't think of everything, costly side effects. It may be better to defer till later, the filling in, so we can think of that like renegotiation. Adversary, non-implemented, I think the analog to non-contractability is non-implementability, which is say that we can't solve, it's not like, machine learning is not magic. It's hard to train a robot to do things, and there are problems we can't solve. We can't write all the contracts that we want. So in the paper, we go through the economics literature in incomplete contracting and sort of say, here's some ideas. They're just speculation about stuff we might be able to take from the economics literature and port over to machine learning, insights for machine learning researchers and ways to do collaborative work. And I'm actually going to just fly through these, like property rights. Property rights are not about giving robots property rights. Property rights are about transforming the value function. So I think you can take the idea of selling the firm to the agent. Is there something comparable in, could you sell Facebook to its algorithms by giving it a broader, the algorithm, a broader utility function to think about? I really am just going to fly through this. Measurement and multitasking, we heard a little bit about measurement yesterday, but the point that it was emphasized yesterday, what you can get, you have to have measurable stuff. Right? But if there's measurable and unmeasurable stuff that you can't just hand over, so I think, Eric, you were saying, give the humans the unmeasurable stuff, but if you can't separate those things out, you need your self-driving car to both avoid crashes and be courteous and flexible with other drivers on the road. Hard to measure and reward that, so you may want to, in fact, reduce your incentives on the measurable stuff to promote your measurables, okay? I'm just, again, let's see, these are all in the paper. So I'm going to, those are what we call weakly strategic AI. That's just ordinarily difference between utility functions, reward functions. Strongly strategic AI is, okay, the AI can rewrite its reward function, maybe rewire its hardware, manipulate humans. We spent a lot of time with people who were worried about that. I want to jump ahead, though, to an insight from relational contracting from the legal perspective. So relational contracting from the law and economics perspective is the recognition that contracts are embedded in an environment of cognitive schema, norms, laws, groups, culture, language, relationships, right? It's embedded. So this is the original Granovetter insight, but it was also what Williamson and McNeil and Macaulay were talking about. So here's this little problem that, again, OpenAI folks put together to talk about problems in AI safety. It's a nice paper if you want to get a handle on this, sort of a grab bag, concrete problems in AI safety. They're saying, here's a problem. We've got a robot. We've trained it up. We're going to say, robot, your job, you're going to reward it for getting boxes from one side of the room to the other. That's the reward function. You train this robot. You deploy it. You put it out into the world. And, oh, there's a vase in the path that the robot has learned. What's the robot going to do? Well, the robot is going to plow straight through that vase because it wasn't in the training environment. The robot doesn't know anything about the vase, doesn't have any common sense, is the way they talk about it, about that. I would say, okay, let's think about this. Suppose you had a human you gave that task, right? You got a human agent, and you give the human the same contract as you've given the robot. You're going to pay the human agent per box. That's all the contract says. You're going to get paid to get those to the other side. Now that vase appears. Well, what's the human agent going to do? Well, the human agent's going to go around that vase. And the question is why? Why is the human going to go around the edge of the vase? Well, how do humans do it? What makes incomplete contract rational for these agents? Well, the agent is going to think, okay, if I knock over that vase, what might happen then? Right? Well, I might get sued by the employer. They might be allowed by the law to withhold from my wages. I might get a bad reputation. I might never get another job. The agent is able to fill in and say, my true contract is actually R minus C. There is a cost associated with this behavior about which our contract said nothing. And this is sort of the key point I want to emphasize. Human incomplete contracting depends on tons of external structure. And so I think what we need to be thinking about is whether or not we can build robots that can fill in their reward structures in this way. Can they pull information from the environment about what would be the response? That requires replicating this human process of reading and imagining and predicting the classifications of behavior. It's the good action, the bad action. If you think about Smith and the impartial spectators, what he's saying we do is we imagine how would I be thought of if I took that action. This is in the theory of moral sentiments. And then you have to get the robot to assign negative weight to the things that are classified by a particular human community as bad versus good. So I think from from here, we can build a research agenda. I think there are many, so I think there's lots and lots of work to be done on the theoretical domain. Good.
Okay. Well, it's thank you for asking me to comment. It's a pleasure to comment on Gillian. As she pointed out, she was my student long ago when she was pregnant with her co-author, who I was hoping I was going to get to meet. Well, did he come? Or he's not here. Well, that's that. He's on the market this year. Oh, okay. On the market this year. That's really a shame. Okay, so so I've never met Dylan except in utero, and and so here we are. And my comments are going to be brief. There's the thesis of this paper, as you know, is sort of that there's a useful analogy between alignment problems in AI and incomplete contracting problems in economics. A lot of what the paper is about really is you know, it seems to be written not just for economists. A lot of it is repeating things that you guys all know: the first welfare theorem, the impossibility of, you know, social choice, all of that stuff. You find little bits and pieces of in there. But the central thesis really is that there's a useful analogy between the alignment problem in AI and the incomplete contracting problem in economics. And the AI alignment problem is that the reward function that the machine pursues doesn't match what humans actually value, because that's just hard to specify to an AI agent. And the incomplete contracts problem is that the objective the agent pursues doesn't match the principal's objective, because that's hard to specify in a contract. So those certainly sound pretty parallel. And that you start with the standard economist's model that if you could specify complete contracts which were costlessly written and enforced, you would get perfect alignment and everything would be great. Now, we've heard a lot about this stuff already. In fact, oh, by the way, the paper also has a summary. A lot of the paper, in fact, I'd say the bulk of the paper is accounting for ideas and results from economic theory, and some that were presented to you here, these examples of knocking over the vase and so on, and learning not to win the race, but to score lots of points. Those kinds of examples are in the paper too. So some of it is just that kind of account. Last night we heard, you know, our dinner speech last night from Doina was about reinforcement learning, and again the problems of, you know, learning by trial and error. With she talked about how hard it was for agents to learn, especially when the rewards were delayed. And Susan talks about this a lot too. I don't think Susan is here today, but the difficulty of doing machine learning, the need for using short-term measures, and the short-term measures often not coinciding with what we actually care about, which are only observed in the long term. And the best we can do is look at things that are correlated. So that kind of thing we've been hearing about, and we've heard about the transfer learning. And transfer learning is, for those of you who haven't studied this stuff yet, you know, for example, you train a machine, if you want to train a machine on a small set of images to recognize a damaged car, you first start by training a machine that recognizes cats and dogs and so on. And you make that that's how you initialized the machine learning to learn about, you know, recognizing damaged cars. The machine seems to be good at doing visual image recognition, and you make that kind of the starting point. But that can lead to distortions that we have no clue what they are. As you see, sometimes you just don't anticipate what the implications are, and that's common sorts of problems. And in these reinforcement learning, as we heard last night, there's also this exploration-exploitation trade-off, that you do some learning, but in the course of learning, if the way the machines are learning, and this isn't what was in any of your examples, but in the course of learning, you're also earning payoffs. The exploration-exploitation trade-off can also affect the learning that takes place. So these are all, by the way, from slides that Doina put up last night. I've just copied. I took a photograph during dinner last night about the things that were on her slides, and these are all the things she talked about. How do we reward AI effectively? How do we interpret what we're seeing, and so on? And those are the same points, I think, or very similar to the points that Gillian was making. And we've also heard both this year and last year many similar points about AI agents, omitted payoff bias. Omitted payoff bias is something like knocking over a vase and not considering that in the payoffs. So, these are the kinds of things that Gillian was talking about that resonate pretty well. Now, I am kind of humble about the possibility of taking ideas from economics and applying it directly to AI. It's much easier for me to assess, when you take ideas from another field and bring them into economics, does it make any sense in an economic context? So as we begin to take some of the ideas that we have in economics and say, should we be using these to train machines, I feel a little less confident. And nevertheless, I still find myself skeptical about the analogies. It's not that I don't find the similarities and the problems to be clear, but you'll see I'm a little bit suspicious about the similarity in the solutions, and I'll try to explain why. So the problems do have closely analogous elements. And in fact, this, Gillian actually has already pretty much done this, but in economics, even simple transactions can require complex agreements. One of the examples in the paper is, why not just write a contract that says deliver 100 pounds of peas next Tuesday and I'll pay $200, but it doesn't say what happens if there's a storm that prevents you from making the delivery, or how much you have to pay if some of the peas are rotten, or this is a highly incomplete contract, and you just can't write things as simple as that. In economics, the sources of misalignment come from things like hidden action and hidden information, or factors that are unverifiable to a court or third party, and one of the things you didn't talk about in your talk either, intentional incompleteness. Sometimes we say, you know what, we'll figure that out when we come to it. We will have aligned we don't specify what we want done. We've tried to align our incentives well enough. And these things have reasonably close analogies in the machine learning context. The reasons for misalignment, and this just replays a slide that you've had up, so I will skip over this. But the slides that you skipped over are the ones I really cared about, actually. And it's the analogies about solutions that seem less clear to me. So Gillian went rather fast over the slides about the weakly strategic and strongly strategic agents. And for humans, there are some inherent incentives that we think about. You might have people who are lazy or who have other interests that they're pursuing, and those are sort of built into them. And if you're the guy who's programming the machine, you don't typically have to worry about that. You don't have to worry that the machine has built in that it would rather hire its son than to hire the highly qualified person. It's not worried about that it would rather teach, that it has a preference for earning more income rather than earning less income, and that some particular day it really wants to watch the football game. Those things just aren't built into the machine, and so you don't have to provide incentives to overcome inherent preferences that the machine has. And to the extent that you're dealing with machines that are already created, perhaps then having incentive contracts for machines that already have preferences that have been built in, that could make some sense. I'm not quite sure how I'm doing on time here. Oh, thank you. That's where I'm supposed to look. All right. So for machines, sometimes machines are acting just like humans, and when they are, or when there's a human that you're trying to get to give the right incentives to machines, then you might want to provide incentives for that human in order to create the incentives for machines. But the solutions that are analogized seem to me to be the weakness of the paper. It seems to me that, talking about giving property rights to machines so that its incentives are aligned, if it can't perceive what the in the Facebook application, if it can't perceive the full effects, it doesn't help to make it the owner. The reason it helps a human to make it the owner is it's then in its interest to figure out what the full effects are and say, gee, what should I, the human then is working out what objective it should be acting to maximize. And the machine can't do anything like that, or at least currently. Formal and real authority committing to limited interventions so that the machine will have an incentive. Well, in the strongly strategic context, where the machine is playing a game against the, as you saw, the example with the boxes, if the machine is playing a game against us, then it's very much, we can analyze the machine just the way we analyze humans. But if you're designing the incentive if you're designing the reward function for the machine, presumably, you don't start with it having an incentive to do something different than what you wanted. I see I'm running out of time, so I thought the really most interesting part to me was whether you could somehow create a larger context to correct the problems that the machines were running into. The story about knocking over a vase and the social norms and the implied terms, I'd like to see those ideas develop, because those ideas struck me as things that might be adaptable in the machine context. But I think I'm pretty much out of time, and that's what I saw. So I will just skip the other machine analogies.